Hi everyone, so in this video I am going to show you how to work on the problems on CLT assignments. So there were two problems on CLT assignment, that is central limit theorem assignment based on central limit theorem. The first one had xi as the service time. So this is problem 1. Service time for ith customer, and it was given that expected value of xi is 2, variance of xi is equal to 1. Y was the total time bank teller spends serving 50 customers. Y is equal to x1 plus x2 plus xn, that means, right? And since xi's are independent and identically distributed, expected value of y is equal to expected value of x1 plus expected value of x2 plus expected value of xn, which is, all of them are same, and n is equal to 50. So it's 50 times expected value of xi, which is 2. It's 100. Variance of y again is variance of x1 plus variance of x2 plus variance of xn, which is equal to sigma and sigma square. So 50 times sigma square is 1, or variance of xi is 1. So that is 50. What we had to find is probability that y is between 90 and 100. Now some of you, there was a typo at one place, it said 110. Some of you have used that, and that's fine. I haven't taken point off for that. So by central limit theorem, we know that y bar follows normal with mean mu and variance sigma over square root of n, or standard error sigma over square root of n. Or I should write, because inside the bracket we write variance, so I should write sigma square over n, right? But what we are trying to find is probability of y, so we can convert it into y bar easily. See, y is my sum of xi, right? So y bar is sum xi over n. So what I'm going to do is, this probability is equivalent to y over n, 90 divided by n, 100 divided by n, right? So which is probability 90 divided by n is 50, lies between y bar and 100 over 50. Now I can just standardize it. So y bar minus mu divided by sigma over square root of n is between, we need more space, sorry. So it is equal to probability of 90 over divided by 50 minus mu, which is expected value of y bar, mu, which is equal to 2 over sigma, which is, so expected value of xi is mu is equal to 2, and variance of xi is sigma square is equal to 1. So 1 over square root of 50, and here you would get 100 over 50 minus 2 divided by 1 over square root of 50, which is probability that z is between negative 1.41 and this would be 0, which is 0.5 minus 0.0793. You can use table to get this probability. Basically you're looking at this area. So you can find the area on the left tail and then do 0.5 minus that. So 0.5 minus area on left of negative 1.41 is 0.0793. So this area is 0.0793 and that is 0.4207. Some of you have also used this. So you're trying to find probability. An alternate way of looking at it is between 90 and 100, right? And by central limit theorem, y bar minus mu over sigma by square root of n is a standard normal. So you can rewrite this as sum yi over n minus mu divided by sigma over square root of n is standard normal 0, 1, or sum yi minus n mu. It's the same way whether you do it here and then do the manipulation, or you do the manipulation on this side and then you use it there in the probability. So sigma over square root of n times n normal 0, 1, which is sum yi minus, so many times this is how you would see this is square root of n times square root of n, so sigma square root of n follows standard normal 0, 1. So sum yi in our case is basically some xi, and this one would be some xi. So this is our y basically. This is our y, right? So it's probability. So I can standardize it. It would be probability that z is between 90, that y minus n mu, that is 50 times, and mu is 2 divided by sigma, which is 1, square root of n, which is so sigma is actually, it should be inside 2 because sigma square is 1. So sigma would be square root of 1 and square root of n is square root of 50. Minus 50 times 2 square root of 1 times 50, and this is again give you the same thing, probability that z is between negative 1.41 and 0. Now if you used 110, this would be positive 1.41 and you would have double probability, 84.26% instead of 0.4207. Right, so that's problem 1. Problem 2, we had to find probability x greater than 120, x followed binomial np. Because we are asking you to use central limit theorem, that's why you're going to use it. Otherwise you could actually calculate exact probability too. So, and we can verify how they are same. They should be very similar because the sample size or the number of trials is decent enough, right? So this is x minus ex. I can standardize it over variance of x, z greater than 120 minus expected value of x is np, which is 100. Variance of x is npq, which is 100. P is 0.1, q is 0.9. It's 90. So 120 minus 100 over square root of 90. And you can do the calculation. If I am correct, it's 1.752%, I believe, or something like that. You can check. So it's basically probability of z greater than 120 minus 100 is 20 divided by square root of 90. So you're just looking at whatever value this gives you, you're looking at the right tail area. Or the other way, so I will leave it for you to finish it. The other way is finding exact probability. So if I have to find exact probability, y is binomial, n is 100 and p is 0.1. I mean, it should be very close because it's the number of trials is pretty large. So it's probability of y greater than 120, which is 1 minus probability of y less than equal to 120. Sorry, n is 1000. Otherwise, how is that possible, right? So it's much easier to find the complementary probability, and this one you can find using AutoStat app, or I'm not sure if there is a table for 1000. I don't think so. So you'll have to use the AutoStat app and you'll get that. And whatever you get here and whatever you get here, they should be very close, perhaps almost same. Now if the sample size was small, it would have been a different story.